it's coming soon there, Hannah, right? Let's go back to the outcomes here and let's just see what we've covered already. Have I derived the impulse momentum equation from Newton's second law? Did that yesterday, that equals that. Have we determined impulse from the area under a force versus time graph? No, we did not. We haven't experimented. Have we solved problems using the impulse momentum equation? Yeah, you did that yesterday. We did fat equals math problems, right? So you've done those ones. Now you've done these.
Not the ones below it.
No, not those yet. Have I done this, relating the impulse momentum equation in real-life situations?
Yeah.
Hitting a ball, catching a ball, right? We've talked about increasing the amount of time so that it reduces the force, or increasing the amount of time as you're hitting something to increase the velocity, right?
Yeah,
So I've covered that, I've covered that, I've covered that. So I'm going to do the area thing today, which is real easy, and then we'll get right into law of conservation of momentum. We may not get to 2D. We may not, we'll see.
They're the exact same thing.
No, once you get into 2 dimensions, you get that vector stuff. So we'll see. We'll see.
Okay.
Let's begin right away, and we'll get as much time as we can. So, we will determine the impulse and area in a force time graph, including constant positive and negative force and a uniformly changing force. So, as always, the area under a graph means something. In this case, this is force, this is time. So what is force multiplied by time? Well, it's impulse. No different than when we had graphs of work and distance. And the area, work equals the force times distance, right? Yes, this should be F, and so this is the work, right? We've done this probably 4 or 5 different times, have we not, where the area in the graph means something? I'm still amazed that, I hate to say this, but like on the last test, I had people that had no idea they had to do the area. Every question that has been a graph has been find the area, you guys. It's the same thing over and over again, it's just called something different. Okay? Now it's going to be impulse. This is page 283 in the book, by the way. So, if a constant force acts over time, and I think your graph needs to be filled in, right?
Yeah.
Okay, so if a constant force acts over time, the basic graph will look like this. The force remains constant, doesn't it? And if this is time, force multiplied by time is the area under the graph. Length times width. An impulse is defined as force times time. Therefore, the area under the graph is defined as the impulse, which is the letter J. The impulse is the area under the graph. And when I say under, if the graph is below and it's negative, then I don't mean under in that sense. I really mean the area between the graph and the time point. Right, Heather? Yeah. Did you need to pick up your phone? Because I'm not really done. Yeah. You got to stop that. Yeah. You don't have to check every 30 seconds. You'll survive. So the impulse is the area under the graph, right? And again, if it's negative, if it's like this, then it's that area there, right? Okay. All good? Yeah? In most cases, though, the force is not constant. If I go over there and I whack Jason in the face, the force is not going to be constant. Okay? I'm not going to do that, though. No. In most cases, the force is not constant and increases as colliding objects are compressed and decreases as they move away from each other. Think about that spring that we talked about before, right? As you compress it more and more, it requires more and more force. So the force is not constant. This is taking a racket and hitting a tennis ball, right? And as you compress the ball, the force increases until it can't compress anymore, and it starts to bounce off, and then you get that rebound effect, and then there's less and less force. So the force is not constant, but that's okay because we've already defined the area as the impulse. Because if it is constant, then it's easy to do. We just have to find the area here, but in this case, it's not going to be force times distance. What is it going to be? Yeah, it's going to be 1/2 the base times the height, because it's the area of a triangle. In this case here, that would be 1/2 the base, which would be the time, 1/2 of 1.2. What's the height? We'll assume that that's at 25. What's half of 1.2 times 25? 15, I think. Am I right? Can someone confirm that? Thanks. 15 what? Joules. Is it joules? It's impulse. Newton seconds. Newton seconds of impulse. And that is equal to the change in momentum, right? And if I said, let's just say that this tennis ball here, let's just say that the tennis ball had a mass of, I don't know, what would a tennis ball weigh? Maybe 100 grams? So what would be the launch speed? What would be the velocity of the ball if it had 15 Newton seconds of impulse? Why not? I'm going to ask you next Wednesday. Mass, as always, must be in kilograms. How do you convert grams to kilograms? If there's one thing that you should know when you leave me in 3 weeks, is how to convert grams to kilograms, my friend. Not 3.6. Divide by 1,000. Oh.
I thought we were doing like the grams and newtons.
It's a good thing I don't get paid by the result. 0.1 times delta V, it's equal to 15.
Pretty fast.
Yeah, that would be going 150 meters per second. How fast does Nadal hit a tennis ball?
That's what happened when I got in the gym.
100. Oh, yeah, that's not kilometers an hour. That's meters per second.
Steve, you're good. And that's not
So, yeah. I'm guessing, which of those two things do you think is most likely to be out? The 100 grams or the 15 Newton seconds?
Probably 15.
Yeah. Would the tennis ball be in contact with the racket for 1.2 seconds? No, that's way too long, right? Yeah. It might be 25 newtons, but it certainly wouldn't be that much. So yeah, that 15 is way too high. Okay, so again, you're talking about area, right? That's what it boils down to. Right? All good? Here's example 4. It's from the textbook. Whether you got the book or not doesn't matter to me. Determine the impulse for each of the given graphs. Here we have a stretched elastic band applies more force than a limp elastic band. The applied force is decreasing over time as the stretched band returns to its relaxed state. So as it becomes less and less stretched, there's less and less force. How much impulse? How are you going to do this when the graph doesn't go all the way down to the time coordinate?
You make a rectangle out of it.
Exactly, Steve. Good. Make a rectangle there and triangle there, right? It's like he knew what to do. What would be the area of the rectangle? It would be base times height, so that would be like 1 times 20. 20
Newton seconds.
Oh, now. What should I do? What's the height? No, that's one of the, I started a bracket. 50? How'd you get 50?
Because it started at 20.
Starts at 20. Very good. So the impulse would be 20, it's 25, 45 Newton seconds. This is pretty easy stuff. In fact, all of these, find the area under the graph, is easy. It always has been. What are the things that are area under the graph? There's this one. There's work. There's distance, displacement, velocity multiple times. There's probably one more.
Velocity.
There's the other one, momentum.
I just need everything.
Mass times. Not often you would graph mass and velocity though.
Right, because mass is
But it
Yeah.
not be velocity. Yeah, I need acceleration. Time graph, velocity.
Yeah, I guess acceleration time graph would be velocity. Yeah, that's true. Yeah, good. Okay. What are you going to do when you get something like this?
Yes.
Well, you could estimate. If you go back to the outcomes, it actually says include constant and positive and negative force, uniformly changing force. When I say a uniform changing force, it means that it changes at a constant rate, i.e. straight line. Changes at a constant rate, straight line. Is this changing at a constant rate? It's not. How would you estimate this?
just split it down the middle and say it's two triangles.
You could just do that. And you could say, well, that little bit there sort of balances that little bit there. Right? You could do that. You could, and this actually, I'm going to blow this up here. Those of you that are in advanced math, yeah, have you done any integration yet?
We're on our last unit.
And what is that?
Well, we might be okay. You might just have a different word for it.
Okay, has he talked at all about like area?
No, we haven't dealt with area one.
No? Okay, so like if you think, oh, okay, yeah, you guys are into that.
Limits.
Limits? Okay, so like if you take this area right here, like you see how there's a little bit that's missing there? Okay, and so if you take thinner and thinner slices, if you imagine at the top, I can't really draw it just now, I should have a picture, but if you imagine at the top, the flat line across the top, there's going to be a little bit that's over and a little bit that's under, right? And if you make it thin enough, then the over and under is so small that it's minimal, and you just say it's the same. So that's kind of the geometric version of integration. Okay? I'm not going to make you do this. I just want you to know that this is non-uniformly changing.
So basically,
Problem there, Heather? Problem? No? I was politely asking to put it down. I need you to listen. Thank you. So you could count squares if you want. You could do as Steve suggested, just call it a triangle. Either way is fine. Okay, or I guess you could go and learn calculus, but you'd have to actually know the equation of that curve. So don't worry about ones like that. That'd be kind of... No, but I wanted to sort of point it out that you're not going to see that. But if you ever do get there, like if you're taking physics university, you can say, oh yeah, I remember doing this in Mr. Bennett's class. Same idea. I remember. Now I get it. Okay. I have... Oh, I didn't run those off. Or did I? I'm going to assign you some questions. They're on page 287 and page 308. I know you don't have a textbook because I didn't tell you ahead of time. I know I run them off, or I printed them out. I just need to find them. So give me a second.
Why don't you keep like 10 seconds?